to do one, not even one, it's already isolated for you, right? You just have to think about your 3 rotations, collect your answers, two cycles around, 2 rotations, collect answers, and a half rotation like we did before. We okay? They were all in radians, so you'll get I think maybe one of them shows up in the chapter review. I have another review that I sent away to the printers. These don't come along that often, to be honest. Most of the double angles or the multiple angles you're asked to solve are the doubles, and you can usually get yourself out of it with an identity, which I think is a little easier, okay? So we're going to do the graphing. This book is a little out of order from what the old textbook that I used, which is why I thought I was going to do graphing before. So if you have your graphing book, pull it out. How many people need another graphing book? Okay. If I run out, I might have to print some pages off for you guys. Okay. Everyone got one? You need one, Carlo? Carl? Why do I always call you Carlo? I think I have a fondness for that name. Carlo. Okay, everyone got one now? Okay, so unfortunately, sorry to make you go back like that, but we are going to do the do you need one now? You still need one? Okay. Can you guys share a book for now? Okay. Let's see. So take a look at, just 1 sec, I'm going to just print the pages. Sorry. Yeah. If you guys just could, yeah, if you don't mind, just, I don't know, I can't quickly find another one. Okay, so I'm on page 19 of the trig graphing book. So it says, and John or Berhane, you should be able just to pull a piece of paper up and just follow the instructions and work on a separate piece of paper. So it says, determine, oh, you got one? Determine a trig function to model and solve a problem. All right, so this ties in closely with the graphing, so it's kind of nice. It'll give us a little more practice with graphing. It's just graphing associated with the word problem, so it's graphing with a little bit of an extra step. So it says a town in BC has the deepest natural harbor in North America. The depth in meters can be measured by the equation d at t equals 8 cos pi on 6t plus 12, where t is time. Sketch the function for 2 cycles. So we should be able to do that. Label your axis and provide scales. So it's, I think, remembering back from your graphing skills, we should be able to do that. Now the reason trig functions are so important in this course is because, as I mentioned at the beginning of trig functions are anything that's cyclical, any data that's cyclical, or that follows a pattern, a wave pattern that repeats itself. So again, lots of physiological stuff within our body operates sinusoidally, like the amount of oxygen we have in and out of our lungs. Some of our blood work is, our heart rate can be followed with a wave sign. So lots of physical things inside our body and lots of physical things we observe outside in the world, especially with due to weather patterns, tides, sunlight, sunrise, sunsets, temperature, right? That's all modeled sinusoidally. So they have huge applications. Probably the most applications of all the functions we've studied would be trig functions. So you're going to see a few of them. So all the natural phenomena I just studied, or I just said to you, can be studied with a trig function. And anything that moves cyclically, right? Like a wheel. Anything associated with a wheel, like Ferris wheels. You'll see some Ferris wheel. We've got a Ferris wheel example coming up. So anything that moves around and around and around, as well as those physical things that we observe. So water depth is can be measured and modeled with a sinusoidal function. So typically in an application, whether it's trig or one of our other applications, the x and the y variables are replaced with something more descriptive, okay? But that's what you have to use to label your graph with. So here d at t, d tells you that d stands for depth and the units are meters. T stands for time and the unit is hours. The word problem should give you the labels and the units to use on your graph. So d at t is replacing the y, right? That's d at t. And that's the funny or the fancy way of saying like f of x, right? And this is t. Now, to get full marks for a graph, I have to label my scales, but I also have to label the axes themselves. So this is depth. I have to actually use the word, and the units is in meters. M stands for meters. And this is time. And again, I have to tell what unit I'm using. I'm using hours. Okay. So what do I need to do a trig graph? I need a maximum value, a minimum value, a median, I guess. Those are the three pieces I need on my y-axis, right? So this is my d at t axis. And what do I need on my x-axis? I need to know, like, I need the period, right? I need the period down here. So let's do my y-axis first. So what will my maximum value be? And how did you get that? D plus A, right? 12 plus 8 equals 20. How do I get my minimum? 12 minus 8 is 4, and my median value is 12. Okay, so your graph doesn't have to be fancy, but it does need to be drawn with a ruler. And it has to be proper scale. So I have to start at 4, go to 20. I'm going to count by 4s then. So 4, 8, 12, 16, 20. That's 12, this is 4, and this is my 20. Okay, I'm actually going to jot in my d value. Like, it doesn't have to be fancy, just... Most of your application questions will be quadrant 1 graphs. See how this changes a bit? When we were doing our just theoretical graphs, we always had the kind of the Cartesian plane. We showed all 4 quadrants. Most of your applications, like I say, will be taking place in quadrant 1. Okay, now what else do I need? I need to know, so that's I've taken care of my A and my D. Now I have to figure out this. My C value is 0, right? There's no shift, no horizontal shift. So coast starts where it's supposed to start. That's nice. What's the period? The period tells you what your x-axis should be, how it should be slotted off. So what would the period be? 2 pi times 6 over pi. The period is 12, right? And what is the period measured in? Hours, right? So the period of this graph is 12 hours. Does that make sense, considering we're measuring high and low tide? Has anyone ever lived on the coast in a coastal town? No, you have to be concerned about high and low tide, right? Especially if you're bringing things into the port and taking them out. High tide means there's lots of water in the bay or the dock area, so you can bring those big ships in on high tide. If it's low tide, there's not enough water for the ships to dock. So they have to only come in and out at high tide. So that probably means if the period's every 12 hours, you're going to have, what, 2 high tides per day? Right? 24 hours in a day? Okay, so we need 12 hours. It says 2 cycles. The period is 12. So probably if we went up to 24 hours, right? So I don't know, can I maybe use 4s again? 4, 8, 12, 16, 20, 24. it's just a coincidence I'm going up by 4s again. 4, 8, 12, 16, 20, 24. So that represents a full day, right? 24 hours? All right, this is a coast graph with no shift. So where does coast start? Maximum value, right? Now the period is 12. So that means coast starts and ends on the maximum value, halfway between 0 and 12. This, I might actually have to do, actually I think maybe I will do my little 2s in between, right? That might help me out a bit. I'm making my scale 2s, 2, 4, 6, 10, 14, just to make it easier to do my little points. Okay, halfway between 0 and 12 is 6, so that's a low point. And halfway between 2 and 6 is 4. That's where my median values are, at 4 and 8. Does that look like a coast graph? The V formation? It does, right? Except I don't draw sharp edge V's. I do my little parabola shape, right? Okay, let's do another cycle. Starts at 12, so it ends at 24. Halfway between 12 and 24 is 18. So that's going to be my middle line. Or sorry, that's going to be my low point, sorry. And okay, so 12, 2, 4, 6, 2. Okay, hang on. Okay, let's start again. Between 0 and 12, low point is 6. Oh, thank you. It should be 3. A little over, right? And 9. Thanks. Okay. Okay, so my high point starts at 12, it ends at 24. 12 and 24. Halfway between 12 and 24, well, 12 add a 6, that's my low point is going to be 18, right? Halfway between 12 and 18 is 15. Halfway between 18 and 24 is 21. There. Okay, so 2 cycles of the coast graph. And it's going to go on and on forever. You could put arrow there if you wanted. I'm not going to put an arrowhead here because it's, why can I put an arrowhead here but not here? Yeah, time can't be negative, right? Okay. So what is the period of the tide? Well, we kind of did that already up here. Period equals 2 pi divided by pi on 6. I get the number 12, but the period is the, like what's on the X scale, so you have to say 12 hours. So then it says, an ocean liner needs a minimum of 12 meters of water to dock safely. From the graph, determine the number of hours per cycle that the liner can safely dock. So they need a minimum of 12 meters. So they need at least this much water, right? It says determine the number of hours per cycle. So, I mean, I may as well use this little piece, right? This is the safe zone. That would be the safe zone for the ocean liner. Safe zone for the ocean liner in part B. Okay, so what did we say? What hour was this again? This was hour 9, wasn't it? And this was hour 15. So from hour 9 to hour 15, which is what, 6 hours? Now, I could figure it out from here to here too, right? 3 and another 3 is still 6, so yes, the liner can dock, can safely dock for 6 hours. Part D, the minimum depth occurs at 6 hours, right? So in 6 hours, it's the minimum. What is the minimum depth? Four meters, okay? When does it hit 4 meters again? Yeah, it hits the minimum depth at what, 18 hours? Which is 12 hours from 6 hours, right? So that's the length of the period, right? It's always gonna hit a minimum every 12 hours, which is the period, right? It hits a maximum. What we started, this equation started at a maximum. 12 hours later, it hits another maximum. 12 hours later, it hits another maximum. So there would be 2 high tide, 2 low tides. You'd want to pay attention to the high tides because that's the only time you can get those ships in and out of the harbor. Right? You'd want to pay attention to the low tides because you can't dock your big ship in the low tides, right? So they probably have some big schedule at those big docks in Vancouver and on the East Coast, I'm sure. Ships can get in and out, what the timing is, kind of like an airport in a way, right? Okay, so that's an application. So applications, you see some high and low tide questions, some temperature questions can appear in sinusoidals. Another type of question that's common to see is a Ferris wheel. Because a Ferris wheel or a bicycle tire or some kind of car tire, the motion that a person like is sitting in one of the carts of the Ferris wheel, or I think we had a stone stuck in a tire on a question that you had. If a stone got stuck in a car tread tire and you somehow could map the stone's distance from the ground, it would also create that sinusoidal function, right? Because it would touch the ground and then it would go up as high as the top of the tire and then down again. Okay, that's what's happening to someone on the Ferris wheel. Okay, everyone know what a Ferris wheel is? You usually see them at carnivals. So what happens is you enter, depends where you enter. I think sometimes you can enter a Ferris wheel on the side if there was a big ladder. Most of the time you enter on the bottom, right? You climb into the cart. The wheel starts turning, and what happens to a person in that cart? They go up, up, up in the air to the highest, the maximum height of the Ferris wheel. Then they start descending and come down. Okay? So, let's see what happens here. Now, you should be able to create a quick sketch and create, now the last time here they gave us the equation. Notice that? This time, they didn't give us the equation. I can see in part B, they want us to write the equation of the Ferris wheel. So let's see if we've got what it takes to do that here. The height of a Ferris wheel above ground follows a sinusoidal path over time. Its starting point is at the minimum height of 3 meters above the ground. The diameter of the Ferris wheel is 12 meters. It takes 16 seconds to make a full trip. Sketch the graph for 2 full cycles, label your axes, provide scales. Okay. So once again, the starting point is at 3 meters above the ground. The diameter is 12 meters, and it takes 16 seconds. So I see the 2 units they gave me were meters and seconds. Agreed? So meters goes on one axis, seconds goes on the other. Where do you think meters goes? Yeah, usually usually time is on the bottom, right? So this is time again in seconds, not hours. And this is height, not depth, but height in meters. All right, we have to use two variables. You want to stick with t for time? What about h for height? I'll go the height at time t, so I'll go h of t. Okay, so we need a maximum, a minimum, and a median height. I think that y values are always the easiest one, the h values in this case. So what, does it give us any info here? It gives the minimum, right? Now the reason the minimum isn't 0 is because you can't have the Ferris wheel starting, you can't have the, if the height was 0, the cart would dig into the ground every time. So normally you climb up a little platform, right? So that would mean if our little picture here, this is 3 meters high, right? Because it says the minimum height is 3 meters. So if this is 0, this would be 3, right? Okay, so my minimum height's 3. It doesn't give us our maximum though. Any idea what this maximum height would be? No? Adam, you said what? Okay, Adam says 15. I agree with him. How'd you get the 15? Yeah, the diameter is 12. Diameter is all the way across, right? But if you think of all the way across this way, add 12, right? This is 12. If I start at 3, add 12, I get 15. So my maximum height is 15. The maximum a person could be in the air is 15. The minimum is 3. So I think I'll count by 3s. I'll go up by 3s. So if this is 0, I'm going to go 3, 6, 9, 12, 15. Okay. If my minimum is 3, my maximum is 15, what's the median? What's the average of between 15 and 3? Remember, D is the average height. So 15 plus 3 would be 9, right? Does that look proper on the graph? Yeah, right? So I'm going to say D equals 9. Now, we're going to be doing our equation after we do our graph. I already have 2 of my values, right? If I need A, B, C, and D. I think I already have, well, I have D is 9. Don't I have A already as well? What would A be? Well, this is the distance of A, right? It could be 15 take away 9 or 6, right? A is the distance from the median to the high or the median to the low, so it's a distance of 6, right? You should, I think it's easy to pick up from the graph, but if you need a formula, it's max minus D. Okay, so now what? I need my period in order to figure out what my scale will be. So, what info did they give us? They told us my starting point is at the minimum. Okay, that's going to be helpful. So that means I'm going to start here, and then I'm going to work my way up. The diameter of the Ferris wheel is 12, so I already used the 3 and the 12. The only other number, numerical value is 16 seconds. It takes 16 seconds to make one full trip. Yeah, that's the period. So it's saying if I start at the minimum, so I guess people board at the bottom, right? They go up, and they come down, and that whole trip takes 16 seconds. That's the period. So whenever it gives you a full revolution or a full rotation, that's your period. Period equals 16 seconds. So let's see, one full rotation is 16. A circle's kind of divided into 4 parts, I think the easiest. So do you want to use 4? as our, right? If you think of a circle as 4 quarters, 16 seconds divided by 4. I'm going to go up by 4s. Hopefully that'll help me. So 4, 8, 12, 16. That's one full period. 4, 8, 12, 16. I just made it. So this is going to be 16 seconds. My end will be 32 seconds. 8. Now you can choose to go up by, excuse me, any scale, but make it, you know you're going to be cutting that 16 in half and then in half again. So I probably should have gone up by 3s for this guy, right? I'm thinking about now, right? Anyway. Okay, now let's plot. It also gave us the idea that the minimum, it's starting at the minimum because you're boarding at the bottom. So you're starting at the minimum value and you're ending, of course, at the minimum value 16 meters later because you want to get out of the cart again unless they give you a second ride. So halfway between 0 and 16 is 8. It's going to be a high point, and then it's going to be a middle. So up. Once you have your scale and you know where your starting point is, it's super easy, right, to draw another cycle. So let's go low and low. Halfway between is high, and then I have middles. Okay, so I got 2 cycles. Once again, I could draw an arrow on the right end, but I can't draw an arrow on the left because time can't be negative. Quite often, things that involve motion, like a physical, like a tire or a Ferris wheel, quite often we end up using coses as the model instead of sine. Does that make sense in a way? Coses start either at a high or a low, right? A minimum or maximum. And typically, when we're talking about something, you're usually going to start at the bottom or the top. I suppose there's things you could start in the middle of a cycle, but more often than not, lots of these application questions end up having cos as the model instead of sine. All right, so we need, we have to do our equation, right? We've got A and D so far. I guess we could figure out what B is, right? B equals 2 pi over the period, which was 16. Yeah, so I could say that's pi on 8. So I've got A, B, and D. I just need C. Okay, C is the shift. And they want it as sine or cos. So it's up to you. Do you want this as a sine or a cos graph? Cos? Okay. So do you want it, what are you going to say for cos then? What is C equal to? If you want cos for 0, I have to say it's a negative cos graph then, right? Cos would be 0 if it was a negative cos graph, a cos with a reflection, because cos is supposed to start at a high if it starts at a low. Or I could say it's 8, right? Eduardo, you said 8, I think. It could be 8 for a regular cos graph, just for a positive cos, because that's the first maximum that occurs. What's another value for a positive cos graph? 24 would be the next one, right? What if I said I wanted you guys to give me a positive sine graph? What would C be? Positive sine. 4 or 20. What about negative sine? Only on something you see. 12 or 28, right? So let's stick with, Well, you decide. What do you want to do? Positive cos, negative cos, positive sine, negative sine. What do you want to do?
Negative.
Positive cos? Okay, so let's do positive cos. Y equals A, which was 6, right? Positive cos for D. And then we're going to do, oh, you know what? Okay, I'll do this first. X minus 8, close bracket. Oops, sorry. Pi on 8 is my B value. Close bracket, plus 9. Now I just remembered something. That would not get me full marks on my exam. Because I was trying to be fancy, and I didn't use X's and Y's, so I'd have to use H at T equals 6 cos pi on 8 T minus 8 plus 9. If whatever variables you use to label your axes, that's what you have to use in your equation. Now, we could have left at Y and X. That might be easier. If you have a choice, then you don't have to worry about anything special. Abdullah, you had a question?
Yeah, actually, how do you say if it starts with 4, you say it's going to be positive sign, right?
Yep, because sine starts halfway up, going uphill.
Okay, so
This is downhill. Downhill is the negative sign. Okay, what's the height of the Ferris wheel 12 seconds after start? Yep, it's right here, right? 9 meters. What's the period of the function? Yeah, 16 seconds. What does it represent? Well, it represents one full trip around. It represents one full trip around. Kind of told us that. Whoops. On the Ferris wheel. Okay. So here's something that occurs quite often, like in an exam. State one limitation on the domain. Okay, remember what domain is? Whatever the x scale represents, right? So what does the x scale represent? It represents time, right? So what's a limitation on time? Yeah, time must be positive or time can't be negative. What if they said, what's a limitation on the range? What's the range in the situation? Yeah, it's between 3 and 15. Like the person on the Ferris wheel, if they're on the Ferris wheel, will never drop below 3 meters or never rise as higher than 15, right? We're hoping. If something happened that they rose higher than 15, the ride's probably broken, right? And they go spinning out. Okay, so applications, they kind of are nice in a way because, like I said, because these sinusoidal functions are so regular, right? They're cyclical. Okay, I'm just going to see what the last one is, Abdullah, then I'll give you my book back. All right, do you want to power through these? You want to power through these last two? Then I'll give you work time tomorrow, I think. Okay. We'll do one more. I'll save example 4 for tomorrow. I think I've loaded enough on you. This is an application because it's got a word problem setting something up. But once again, they've given us the equation, right? So that's half the work done. I think I'll do example 3, then I'll let you guys just finish up whatever you were working on today. We'll talk about 4 tomorrow. So the alarmative factor is a siren whose volume fluctuates so that t seconds after starting, the volume is given by the function. V at t is 18 sine pi on 15t plus 60. Very complicated equation. But sound also travels in waves, right? Sound reaches our ears in wave formation, so that's another example of a use of a sinusoidal function. When we say sinusoidal function or wave function, that includes sine or cos, right? They both travel in waves. Okay, what are the maximum and minimum volumes of the siren? Okay, take a sec, give me the max and minimum volumes of the siren. What's max? Okay, 78 and 42. All right, so how do we get that? How did you get the max? D plus A, right? Min D minus A. Okay, so start here. This is your minimum value. Whatever the absolute value of A is here, it's positive, so I didn't have to worry about taking the absolute value, but 60 plus 18, 60 minus 18. Okay, don't forget because these are applications, there will always be units, so add your units in. What's the period of the function? Yeah, so I do my flip, the pi's cancel, and I get 30 seconds, right? So that's the period of the function. So whatever kind of high-low sound goes through that siren, because sirens have kind of different sounds, right? You can kind of, you can tell the difference between a fire truck siren and an ambulance siren, right? So they go through different patterns, I guess. So this patterning goes from a high to a low in 30 seconds. Then it would start to repeat itself. What's the volume of the siren after 60 seconds? Okay, well, how would I figure that out? Yeah, this is time, right? This represents time. So substitute 60 in for T and just solve for V, right? Solve for volume. Now, let's see if this is an exact value that we could do without a calculator. I'm not sure. So the volume at T is 60 would equal 18 sine pi on 15 times 60 plus 60. Okay, so what's that going to give me? 18 sine. Okay, so 60 divided by 15 would be 4 pi, right? I think we could do this one without a calculator. What's sine of 4 pi? 0, right? 18 times 0 would be 0, so it would just be 60 decibels. That's a coincidence, by the way. At 60 seconds, we get 60 decibels. So that's not quite maximum decibels, right? But maximum is 78, but it looks like it's approaching the max, or it just achieved max volume. Yeah.
Or we could just imagine
That's true. This, right?
Yeah.
We could almost figure it out this way, right?
then a period would be in the middle, right? Because it's a sign.
Yeah, perfect. Now, this one says draw a sketch. So, unlike here, like previously it said, sketch the function for 2 full cycles. Let's try just a rough sketch, okay? Let's try a rough, meaning kind of minimizing. So this time I'm going to say to you guys, we can even get by maybe without being so precise in our labeling, but let's see how we could get by if we kind of just wanted a quick sketch like Carl was thinking of, just to kind of answer a couple of questions even, right? So my bottom is going to be time again in seconds. And this is the volume in decibels. Okay. So we're gonna do, let's even do this one without even doing proper scales. So what do I need? I need a min, a max. So I'm gonna do this. This is how, I'm gonna flip it. Didn't give myself lots of room on this graph, right? So min, median, max. This is what I mean by proper scale. So I'm just gonna put a 78 here, a 42 here, and a 60 here. Okay, those are my three important numbers. It's not proper because I didn't measure from the corner. Okay. The period will tell you how you're going to break up your x-axis. So the period is 30 seconds. So I go through one complete rotation in 30 seconds, right? 30 doesn't really divide nicely by 4. So I guess we'll do it anyway, right? So I'm going to say 30, 60. I'm just going to cut things in half this way. Whatever they give me for a period, I have to divide nicely by 4, right? So let's say this is 30 seconds. This would be 60 seconds, right? Halfway between is 15. Halfway between would be 45. Just gonna kind of do a really quick little sketch here. This is my middle. Now there's no shifting, right? So this graph would start, sine starts on the middle, and it ends on the middle. Halfway between is another median, and then I have a high and a low. Repeat. Okay, so that would be my real quick sketch. Now let's check what Carl said. He said he kind of solved it. You might not have actually sketched the graph, but you were visualizing it in your head, which is awesome. So he answered this question just visualizing in his head the volume after 60 seconds, because it had said that it had done, what did it say? Or we calculated it was 30 seconds. You kind of just doubled that, right? You just went, okay, well, if it's finishing up at 30, sine ends on the middle, it's going to just do that again for the 60, right? You're thinking that in your head. Perfect. Okay, so once again, I think I threw a lot at you. We're going to save this last one till tomorrow. So we'll talk about that one tomorrow. So finish up. If you didn't get your homework finished, finish up the homework, look at the chapter test. There's also, so tomorrow, the work period. We'll talk a little more about your test on Friday too. So just before the chapter test, there's some application problems. I'm going to give you time in class to work on those tomorrow as well. So you can see there's, I think you could work on all of these. We've got a tide problem, minimum maximum depth. We did one of those. Ferris wheel, and then a time of sunrise.